Okay, so now I wanted to talk a little about the non-standard methods in geometry. Namely, about the metric space. So metric space is a pair x and d. So x is some set, d is a distance function. So for xy, you have d of xy more equal than 0. No, and the general property that d of x equals 0, d xy equal d yx, and the triangle d xy plus d yz more or equal d from x to z, triangle inequality. No, I would say, simplest example of metric spaces are graphs. So what is graph? We have a set, one set V, set of vertices, and E is the set of edges. So if E in E is just a pair x, y, where x and y so let me denote graph of course by G. No, xy in the V, in the set of vertices. G is this pair V and E. In simple cases we can draw the picture. These are the vertices, and some of them are connected with the edges. Yeah. No, maybe some vertices are idle. I would say that what is seriously interesting graphs, of course, are very universal thing, but seriously interesting is what is called Cayley graphs. What is Cayley graph? Suppose you have a discrete group. So V, G, discrete group with generators, say G1, G1 minus 1, Gn, Gn minus 1. So any element of the group can be represented as a finite product of these generators. Yes? And so in this case, V equals G. So each element of the group is a vertex, and the two elements of the group are connected in the following case. So x, y in V if y equals x times g k, no, plus minus 1, either gk or gk minus 1 for some k. Yeah. So we multiply x by one of generators. Now, for example, is when our group G is the group of integers. It has just two generators, plus minus 1. So it is a Abelian group with the addition as a group operation. And so we have G1 equals 1, G1 minus 1 is minus 1. Yeah? And so every element of this group is a result of multiplying by, let's say, of adding some number of ones or minus ones. So in this case, we have this graph. Yeah. Now, similarly, G equal Z2, just the lattice, the set of pairs. Yes. So the points are integer points in the plane, points with integer coordinates, and so on. And of course, to add, so here we have this is G1, this is G1 minus 1, this is G2, this is G2 minus 1. And so we can move either right or left, or up or down, every time when you apply this operation. And so our graph is this. So the vertices are integer points with integer coordinates, and the edges are either vertical or horizontal edges. Yeah. No more maybe exciting example. So in this example, you have the following: G1 plus G2 equals G2 plus G1. Yeah, so it is a commutative. Now I write the group operation as addition. And therefore, we have so many closed loops here. Yeah? Let's consider F2. It is a free group with two generators. So we have G1, G1 minus 1, G2, G2 minus 1. So we have, no, in fact, we have two pairs of generators, G1, G1 minus 1, G2, G2 minus 1. And we have no such relations. No relations. So any string of G1, G2, G1 minus 1, G2 minus 1, if it cannot be simplified when two, say, G1 and G1 minus 1 stay together, then one after another, then we can cancel them. Each such string is different from any other, so I mean it gives a different element of group. So we have element E. Now we can apply, let's say DE, we can apply G1, we can apply G1 minus 1, we can apply G2, apply G2 minus 1, and have these four elements which are the neighbors of this. Now for this element we can apply again G1, we can apply, if you apply G1 minus 1 we return here. So we apply G2 and G2 minus 1. So we have three new elements which are connected with three edges. Here we can apply G1, G1 minus 1 and G2. And the same here, yeah, and here. Now we can look at these elements again. We can apply G1 and G1, G1, G2 and G2 minus 1. Here we apply G1, G1 minus 1, G2. Here apply this. This. Yeah, so we have this picture. No, okay, we can continue this way. So we have a countable set of edges and countable set of vertices. Yes, no, they form such a tree. So such picture is called a tree. So what is a tree? Tree is a graph having no closed paths, no loops. Yeah? This means that from any point of this graph to any other point, if there is a path, then this path is unique. We cannot go by two different paths. Otherwise, if you could, you could have a closed loop. For a free group with two generators, we have this Cayley graph is a tree. So this is a graph. For a graph, the set of the vertices of the graph can be given a metric. So, metric in a graph. So, if you have a graph, it is V and E, yeah? So we have X and Y element of V, so two vertices, and we consider all the paths, X0 equals X, X1, and so on, Xn equals Y, such that say xk plus 1, this pair in E. So every time we go from one vertex to other vertex, if they are connected by an edge. Yeah. So we have, say, this graph, something like this, and we want to go from here to here, and we go, say, along this path. Yeah. And consider all such paths. Here we can find another path, say this one. Yes. And define, okay, let me erase this beautiful picture. dxy equals minimum of n. All paths connecting x and y. Yeah. So paths x0, xn. Yeah. No, I assume that graph is connected so that for any two vertices we can find such a path. Yes, otherwise we have two disconnected graphs, and so it's not interesting. It's interesting to consider connected graphs. Yeah, so with this, of course, the graph becomes a metric space. Yes, no, maybe I will ask to do it as an exercise. So what can be done with the graph? No, it can be done a lot, but it is one of the most popular objects in today's applied science, different graphs. But I'm interested today in one result, classical result, which I will tell you now. As you could see, from the very beginning, I introduced some infinite graphs. So these Cayley graphs of groups, these groups were infinite. Now sometimes graph is finite. Now finite graph is not so interesting. I'm interested in infinite graphs. Yes, and in particular, it can be infinite tree, like which was shown here. And I give a definition. A graph is how to call it? Locally finite if for any vertex x v there exists just a finite set of edges with x an endpoint. Yeah. So the graphs which I showed you all are locally finite. No, I can show you example of a graph which is not locally finite. We have, say, x, and you have here a countable set of points y1, y2, and so on, yk, and so on. And we connect this point x with all these points. Yeah? So this graph is not locally locally finite. Yeah? And for locally finite graph, I wanted to tell you one famous result. It is called Shnirelman. Suppose gamma VE is an infinite graph which is locally finite. Like which was. And let us take x0 some x0 it is some vertex here. Then there exists infinite path x0, x1, and so on along the edges. So each transition from x0 to x1, from x1 to x2 goes along some edge. So this is what is called Shnirelman. Okay, now let me go to proof. There exists proof which does not use the non-standard analysis, but I wanted to show on this example how the standard analysis can work here. Now, first, what I wanted to say, if gamma is an infinite graph infinite and locally finite graph, then the function d of x0 x, it is a function, say, phi of x, is unbounded. So this function is unbounded. No, no, the proof is the following. If you have a metric space, then you can define what is a ball. X0 R, so the set of x in V such that distance from F0 to x is less or equal R. So now it is like a ball in any space, say in Euclidean space, so it is, and so lemma for any finite R, no, R is integer because the distances all are integer, then R is in N. The set B F0 R is finite. No, okay, why? B at 0, 0 is just the set of one point at 0. Yeah? B at 0, 1 is finite. Because the graph is locally finite. So the point x0 has just finite number of neighbors. Yeah? Now, what is b of x0, 2? To reach it is x0, let's say x1, then we have to make one more thing. Here it can branch, of course, but it is the union of b of x1, 1 for x1 in b of x0, 1. Yeah. So to reach the element, the vertex, which is at the distance 2, we have first to make one step and approach it to distance 1. Yes? This means that we have to take all x1, and then for each of x1 you take these elements. No, in particular, some of these elements can belong to some other ball B, say x2, 1. Yes, it can happen. So, but union, some of these sets can have intersection. Yeah. So it is finite as a union of finite set of finite sets. Yeah. Now and so on by induction. B of x0 n plus 1 is the union B x1 1 and x1 B of x0 n by the same principle. Yeah. So at every step it is the same. Finite is a union of finite number of finite sets. Okay, so and if our gamma is infinite, and if every ball with finite radius is finite set, this means that there are elements beyond this ball. So for any n, there are elements which are at the distance larger than n. So this lemma is proved. Now, again, let me consider a counter example to this our theorem. So I wanted to prove give example of a graph such that this graph is infinite, this function is unbounded, and nonetheless it has no infinite path. No, the example is the following. We have, say, it is x0. We have here one edge. Here we have two edges. Here we have three edges, and so on. Here we have the chain of n edges. It is 1, 2, 3, it is n edges, and so on. Yeah? So here the distance from here to x0 is n. Yes? And this n is unbounded. So this is a graph which is infinite and with unbounded distance function. And nonetheless, there is no infinite path, because if you go from x0, then we cannot go infinitely far. Each of these directions ends somewhere at finite distance. Yeah? So this condition that the graph is locally finite is important. Now we have to prove of the string Z. Consider, so our graph is the set of vertices and the set of edges, this pair. And consider its non-standard counterpart. It is non-standard object, yes, which is, after all, union of non-standard V and non-standard E. So, no, what it is, we have, let me return, we have to consider index set I with ultrafilter F, yes, and consider the set function f of I equals, say, pair x of I and edge E of I. It is elements of V, it is element of edges. Yeah? So x of I is this. Two such sequences are equal, define the same element if the no, I'm sorry, something. And G of I equals E of I in E. Yes? No, they are defined almost everywhere, and two such sequences correspond to one element in the set star V if and star E if they coincide almost everywhere on the set which is in our filter. Yes? And I say that F, say, 1, F2 belong to star E, F1 and F2 is X. Let me write. F1 of I equals X1 I. F1, F2 of I equals X2 of I. 2 of I. So two such sequences, and the pair F1, F2 belongs to star E if and only if the pair X1 of I and X2 of I belongs to E for almost all I. Yeah? So this way we define the this set star E. Star E is defined through the no, this way. So it is the standard way how we define the non-standard extension. And if you have how to now to extend the distance function, star D between F1 and F2 equals is defined as follows. Say G of I equals distance between X1 of I and X2 of I. Yes? And G of I is a integer g from I to n. So it defines as a non-standard integer. Yeah? Which is, no, g is defined up to a set of measure 0 in I. Yes, so this is a non-standard integer, and this is integer is what I write here. So g is 1. So we have now this non-standard, I would say, extension of our graph with the graph distance. Okay, now we have the following property. For any, let me write it in our language, any n in n, there exists a function x0, x1, xn, such that, first of all, okay, this is a path along the edges of gamma, yes? No, it is a shortcut. So it looks like for any k between 0 and n, xk and xk plus 1, any k in n such that k less than n, the pair xk plus 1, this pair belongs to E. Yes, it is the same. So there exists such a path such that for all say k, all j in our all k less than n or equal all j less than n, k different from j, we have that xk is different from xj. Yeah? So this is path without loops. Yeah? Now if we have a loop, we erase it. So it is a path without repetitions. This is because our graph is connected. Our graph is and the function distance function from the point x0 is unbounded. So there exists a point at the distance exactly n for any n. Yeah? And now we use the transfer principle. by transfer, the following is true for any n in star n. The sequence x0, xn, there exists, say, a map from this set to the set star V, yeah. X is a path along the edges. It means this with n replaced by star n and e replaced by star e, and without repetitions, without, let's say, without loops. So every term in this sequence x, in this every value of this function appears only once. Yes. So this is true by the transfer principle. Okay, so we have a path of the. Now let me write about x k in star n, and k less than n. In particular, let us choose n star n minus n. Yeah, so infinite n. There exists x k the path connecting x0 and xn. Yeah? The path along the edges. And now let us look at the beginning of this path. So x0 is given. Consider x1. So what is x1? In fact, this path is also a function it is a function the following. X0, xn. What is this? We consider the function, say, h of I. For any I, we have the following. Say, so our ultrafilter, our index set is just n. Yeah. So h of I is x0, x1 I, x I, yeah? Pi. So, what is the infinite path? Yes, we have to consider the sequence of finite paths, such as the length of this path goes to 0 almost everywhere. So, for h of I is the path of the length pi. Yes? Now, this index, say, because in the joint part, they can be different. And now what is, we have this x1i, yes? So we have this sequence x1 equals the sequence x1i. Yeah? But x1 can take only finite number of positions. Yeah? So we have only finite number of neighbors of x0. Yeah? So the index set I can be partitioned into finite number of subsets. Yes, where x1i is the first neighbor, the second neighbor, and so on. Yeah? And if the index set is partitioned into finite number of subsets, then just one of them has measure 1 and the other have measure 0. Yeah? So this means that it is, say, x1 bar for some bar almost everywhere. So there is a property of ultrafilter that if, we start from the fact that if you partition our index set into two subsets, then one of them has measure 1, the other have measure 0. Yes, and then prove by induction that this is true for any finite number of elements of this partition. Yeah. So this means that x1 is found. Yes, please.
Measure of finite number is equal to 0.
Excuse me.
Measure of finite. Measure of finite.
Yeah.
That is equal to 0. That's why you said almost everywhere. You're right here.
Almost everywhere. Yeah. So x1i equals so this function of I. This function takes only finite number of values. This means that it is equal to one of these values almost everywhere on some element of filter. Because if it is not almost everywhere, it is if the set where it takes, say, the first value is not in the filter, the second not in the filter, and so on, for all of them, then they all are not in the filter, yeah? Okay. And the measure is finitely additive, the measure of the filter, yeah? So if it is 0 on each of these sets, it is 0 on all of the filter, yeah? Which is contradictory. So it should be 1 exactly on one of these sets. Yes, and so we found some x1, yeah? And similarly, we find that for almost all of these sequences, x2 is just one element, and so on. Yeah? For all finite indices, we have have chosen this way one element of this index. Yeah. So x0, x1, xp is uniquely defined for all finite p. Yeah, because this reasoning works only for finite sets. Okay, this is what we found. This is what we wanted to find. So, x0, xp can be defined for all finite p. Yeah. Now, if you have x0, xp, and then you have found x0, xq, and say u more than p, then no, these two sequences coincide up to p. Okay. So this way we have a family of finite sequences, but of unbounded length. Yes, and any side two touch sequences where they overlap, they coincide. So there is just one sequence which goes to infinity, which is infinite. So this is the proof. So in this proof, it appears that we we constructed it, I would say, constructively. Yes. But in fact, it all again boils down to a lot of choices which were in construction of the ultrafilter, this infinite number n, and for any finite n we found some path of length n. It is also more or less arbitrary, so it depends on a lot of choices. Yeah. So this theorem, in fact, this lemma does not require the full strength of the axiom of choice. It can be proved by itself without so many axiom of choice, so it is weaker than axiom of choice. And in some works on set theory and logic, instead of axiom of choice, we can use this lemma, in some clever way. But anyway, we already committed this sin, used the axiom of choices many times, so let it be. Okay. And now I'm going, as long as time permits, to the main topic of what I wanted to tell. It is asymptotic space at a point and at infinity. So suppose we have a metric space. No, this metric space can be even some set in the plane, for example, or some Riemannian manifold, something like this. Then it can, our concern is how it is organized near a point and how it is organized at infinity, how it looks at infinity. Yeah? Now, if the space is unbounded, then the second question, how does it look at infinity? And if it is bounded, then we can ask how it is organized at a point. These are two related questions. So how can we try to concretize this question? No, for example, if you have a smooth curve, yes, and take a point here, and we want to know how it is, how it looks near this point, so we can take a small neighborhood and then inflate it, multiply it by some number. Yeah? The idea is, let us take the non-standard version of this, non-standard extension of this curve, everything is non-standard, and let us take infinitesimally small neighborhood and inflate it to a finite size. It is possible. So we multiply all the sizes by infinitely large number. Yeah? Then for a smooth curve, of course, what we'll see more or less a piece of a straight line. Not a piece, but just a straight line. Yeah? So we can say that smooth curve is something which locally, under this microscope, looks like a straight line. Yeah? If, for example, the curve has an edge and a corner, yes? Something like this. Then, if you put it under the microscope, we'll see also just a chord. It's okay. But some sets are not so trivial. No, for example, if you take a counter set, yes, and take some point of counter set, and then perform this operation, the result is not so clear. So this is the local structure of a set if you look under the microscope. If the space is unbounded, then you can use a telescope instead of microscope. Yes? So you consider our space X D, and let us consider the space X epsilon the same X, and we multiply it by small number d. No, for now epsilon is small positive number, or standard. Yes? So if our space is unbounded, if X is unbounded, then X epsilon is unbounded We simply take unbounded function multiplied by small but positive number, it remains unbounded. Yeah? So we have another unbounded set. And the program is the question. What is limit of this set x epsilon when epsilon goes to 0? So we take in unbounded space, we find more and see what is in the limit. Yeah. So if this limit in some sense is defined and exists, then it is what we can call the asymptotic space at infinity. Yeah. So we have here a sequence of unbounded metric spaces and ask what is its limit. Yes, it's a bold undertaking. The question was, I think, first posed by great geometer Misha Gromov. And he gave the first definition. It still did not use the language of non-standard analysis, but used already the language of ultrafilters. And now let me give a definition today, and we will go with this definition and see how it looks for different interesting spaces next time. So I give a definition. Let me define it. X theta. Say definition. Let star x star d. So we define the non-standard extension of our space, and now we define let epsilon infinitesimally small, no epsilon positive but infinitesimal number. Yes? And consider the space epsilon is star x epsilon times star d. Yes. And so this is non-standard thing, and by the transfer principle, there is also unbounded space already in the non-standard sense. So for any non-standard distance, there exists a pair of elements of star x which are at the distance more than this, even if the distance is infinite. And we somehow find the standard part. of star x epsilon. How can you do? We have a point x0 was an element of x and x, and so star x0, which is the same of x0, is element of star x. So we have here some base point already. And let us define temporarily y equals the set of x in star x such that star distance of x0 x is bounded. So it is a non-standard number, but this number is less than some positive standard number. So such numbers are bounded. Now I define the following relation. We say that, say, x equivalent to y. If you take xy in star x, x is equivalent to y if star d of xy is infinitesimally small. So this is equivalence relation. If we fix x, then y is, say, in the monad of x. Yeah? And let us take y. Y is is a metric space, non-standard metric space. Consider x bar equals y factorized by this identity relation, equivalence relation, yeah? So there is set x bar. And we take, if you have, say, x tilde, y tilde in x tilde, so are two equivalence classes. Yes, let us take x in x tilde, y in y tilde, then we have we define delta of x tilde y tilde equals standard part of star d of xy. So we have two these monads, two classes. So each two elements here are infinitesimally close, and these are infinitesimally close. Because of the triangle inequality, if you take any x here and any y here, then the distance between them, if I take the standard part does not depend on the choice, because if you change x here in this domain monad and y in this monad or in this class, then the distance will change by infinitesimal. So we can, if you take the standard part, it will erase all these differences. Okay, now we have defined x tilde is x tilde and delta. Let me denote it for uniformity d tilde. D little. Yeah. So this space is called an asymptotic space of x at infinity. So, no, at least this is a reasonable standard object which is no, some substitute of the limit. We cannot define a limit in other terms. I know no other definition, but this is reasonable definition of a limit. That's it. So result is some standard metric space. No, it is a metric space. There is a metric because all the properties are obtained after all by the transfer and combination with the standard part. So you can just look and see. The main application of this is to the Cayley graphs. So we started from graphs. Graph which corresponds to some group is called Cayley graph. Yes, and the properties of the group are somehow encoded in geometry of the Cayley graph. And the most important properties, especially important in geometry and topology, are encoded in behavior of this graph at infinity. How, no, roughly speaking, how does this graph grow when you go farther and farther? Say, if you take the ball of radius r, it has a finite number of elements, but this number grows as radius grows. Yes, how fast does it grow? Yes, it is one of the questions related to these asymptotic properties of the group or of the Cayley graph, what is now called geometric group theory. So this is now one of the most popular topics in geometry, topology, and so on. I personally also am interested in some groups, not this, but some other groups, maybe more tricky, which are related to fluid dynamics, of course. Yes, and the question, what is the asymptotic space of the groups is now, not only now, but for a long time, I'm working on it. So it is the topic which I'm quite interested personally. So next time I will consider some examples, and if you take a little more advanced example, it will lead us far enough into non-standard analysis or non-standard geometry. It requires some new tools on non-standard analysis. So we will finish for today.